Okay, question 23, we move on to electricity. So you can see immediately that we're going to have some internal resistance in this circuit. We've got a pair of resistors in parallel with an ammeter. It tells us that the resistance of A is 1.8, so just doodle on your diagram. And the resistance per unit length of B is that, and the length of wire is 40. So we just want to quickly work out what the resistance of the second resistor is. So 9.5 times 40 divided by 100. So we got 3.8 ohms there. Okay, so working out this resistance here, that'll be one of our 4 marks. Calculate the current in the circuit. So the current here is being driven by an EMF of 1.4 volts, and there are these 3 resistors in the circuit. So we just need to work out what the current is as a result of these 3 resistances. So these 2 here are in parallel with each other, the circuit branches at these points. And this parallel combination is in series with this resistor here. So we just need to work out the parallel combination first. So that's 1 over 1.8 plus 1 over 3.8, and then we just need to take the reciprocal of that. So we've got 1 over 1.8 plus 1 over 3.8, which is that, which gives us a resistance of 1.22 ohms for the parallel, and then we just need to add on to that the resistance of the internal resistance of the power pack, which gives us 1.84 for the total resistance of the circuit, and then we've got V equals IR. So if we want I, we just need to divide 1.4 volts by the 1.84 ohms, and that gives us 1.4 divided by 1.84 gives us a current of 0.76 amps. Okay, then it wants the ratio of power dissipated in the internal resistance and power dissipated by the cell. So you remember your power formula, you've either got P equals IV, or P equals I squared R, or P equals V squared over R, whichever one works best for us. So in this particular case, power dissipated by the internal resistance, the current through the internal resistance is the 0.76, and we've got the resistance, so it seems this formula would be the best for that one. So 0.76 squared multiplied by the 0.62. So that will give us the top line, and then the power dissipated by the cell, well, we don't have the resistance of the cell, but we do have the potential difference of the cell, which is 1.4, and we do have the current through it, which is 0.76 times 1.4. So we can get rid of one of those, and we've got 0.76 times 0.62 divided by 1.4 gives us a ratio of 0.34. When you do ratio questions, by the way, regardless of how you express ratio in maths, it has to be a decimal. You have to work it out in physics. You have to actually tell me what the decimal answer is. Okay, part B. This is the IV characteristic of a filament bulb, and we're told that we've got 4 of these identically, and we've got 2 of them in series here, and 2 of them in parallel here. And we've got the current running around the circuit, the total current, and it tells us that the current in the parallel circuit is around about 3 times bigger than the current in the series circuit. And can we use this graph to explain why? So what we need to appreciate is that in this series circuit, the 6 volts will be split evenly between the identical bulbs, so they'll get 3 volts each. So if we have a look at the graph and we come up 3 volts and across, we'll hit what, 3.36 amps, so 3 volts each, 0.36 amps. And ideally we would doodle on the graph so that the examiner can see that we have used the graph. In this one, they're in parallel, so each one of them gets 6 volts. So then we have a little look on this, and we can see that they're going to get 0.5 amps each. But that's 0.5 amps here and 0.5 amps here. So this implies that we've got IP is equal to 1 amp, whereas this one is IS. And then we can just show that, I don't know, IP divided by IS equals 1 divided by 0.36, which is equal to 2.7, which it says almost 3 times greater, and 2.7 is. I'm sorry you can see that. So what are you getting your marks for here? You're getting your marks for realizing that that's 3 volts each and that's 6 volts each, that you're pulling off the 0.36 amps, you're pulling off the 0.5 amps and then doubling it to the 1, and then you're doing a quick calculation at the end in summary just to show that you do have a ratio of around about 3.